Morning, everybody. I'm your chairman, and I have to be very short because we are in an extremely short time distance because people have to go take taxi, go to the airport. So I skip the introduction, and I give the word now to Luis Rebelo.
That contributed to this work and that are identified in the abstract. So it's not going to be only on water. It's going to be on liquids, and then I'll talk. I will be shifting between water and other liquids at deep negative pressure, so under tension. We heard yesterday and the day before talks, well, Jerry included, he talked about muscle filaments, right, under tension, so sort of one directional tension. What I'm going to talk is about isotropic tension, so tension in all directions, in liquids, which in the case of thermodynamics, we don't call it tension, it's pressure. Because even van der Waals, in his celebrated equation, predicted that negative pressures exist and liquids could be under negative pressure, and that was forgotten for more than a century. So this is a good illustration of tension, right? It's a beautiful sculpture by Roxy Payne that is in Washington, D.C. And tension means also that I'm going to stretch liquids in all directions. The next slide is not about water or aqueous solutions, it's about ionic liquids. I will briefly explain later what an ionic liquid is, but basically it's a liquid salt. And I'm going to tell you, this is almost the end of the story, I'm going to tell you what were the initial results. So we had a sample volume of about 0.05 cubic centimeters, and we were able to produce these negative pressures. And to give you an idea, this means that per each 100 bar, in this case minus 100 bar of tension, the volume, the molar volume variation of the liquid is about 0.5%. So you can extrapolate, if you reach minus 1,000 bar, you basically can multiply this by 10 and you get a 5% effect, which is a lot. Because this is almost close to the volume increase we have in water when it freezes. Well, it's half of that, but it's a lot because the water is in the liquid state, is not in the solid state. So with water, you can achieve these tensions of about minus 1,000 bar, but you have to have very, very, very small volumes, like crevices, pores in natural rocks, or things like that. For macroscopically sized volumes like this type of volumes, like 0.1 cubic centimeters, it's almost impossible to do that. But with these liquid salts, you can achieve these very deep negative pressures. So if you look, this does not matter much, but look to the highlighted in red columns. So these are acronyms for ionic liquids, don't care about that. And these are examples of pressures that we were able to obtain. So in some cases, minus 100 megapascal, so minus 1,000 bar. In the next slide, I'm going to explain to you how is the phase diagram of a metastable liquid. So I'm starting with the normal phase diagram. This is not even for water. For water, we have a negatively sloped melting line, as you know, but doesn't matter. This is a general concept. So you have the solid, you have the liquid, you have the gas, you have the critical point, the triple point. Now, it occurs that the liquid is a very promiscuous phase. Why? Because it always wishes to invade the territory either belonging to the solid or to the gas. So the phase diagram of a metastable liquid looks like this. So there are no lines of equilibrium anymore. The liquid is occupying basically all the phase diagram, and what you have here is the spinodal line. So beyond this spinodal line, the liquid cannot exist. It will collapse. But this is the limit of maximum tensile strength. So it's the limit of mechanical stability of a liquid, where the response functions like expansivity, compressibility, etc., diverge to infinity. Now, if there are no y axis here or scale, but we can do that. So I can put here a line and say this is the zero pressure line, okay? So we have positive pressures here, negative pressures here, and this distorted rectangle is the forbidden land, right? Because the liquid, the gas cannot be put under tension, so the gas cannot exist at negative pressures. Only condensed phases can be stretched due to the strong intermolecular forces. A gas phase cannot be stretched. Now, how do we provoke negative pressure? I'm going to start with a very simple, student's textbook kind of projection of the phase diagram, the PVT phase diagram on the PT plane. And I'm going to put here a typical vapor pressure curve. This could be for water. And as you know, independently of this liquid vapor curve, we also have an infinite number of isocores. Isocores are constant volume lines. So we have infinite constant volume lines along crossing the vapor pressure curve. So let's start also with something we can do in a lab and showing this to students in a lab. So I have a glass capillary here, filled with water, closed at both ends, and you can see here a bubble. It's the vapor pressure. It's a small bubble containing the vapor pressure of water. And I'm starting this experiment at 24 centigrade. So we are already somewhere here at the 24 centigrades in the liquid vapor equilibrium line. If I warm up my sample, if I increase the temperature, at a certain point, due to expansion, my water is going to fill completely my capillary, right? So the bubble disappears because it dissolves, the gas phase is completely dissolved in the liquid. If I continue rising the temperature, let's say up to, in this case, 52 or 53 Celsius, I'm building positive pressure, right? The liquid is trying to expand, but it is in a constant volume environment, so I'm at normal positive pressures. Now, if I start to decrease the temperature, what happens, probably you have not noticed, but when we were at point B, where the liquid initially filled completely the glass capillary, we were at 50 Celsius. Now we are at 35, and there is no bubble. So the liquid is expanded. It's in a metastable state, right? What you would expect is that crossing again the B point, a little bit below, a bubble should form somewhere, or several small bubbles. I can continue even this deeper. So now I'm at 32 or something like that. And again, the liquid is occupying the entire volume. So you can see that there is an expansion because here you have all this volume occupied by water, while at the same temperature, the corresponding point over the liquid vapor line would give you a smaller volume because there would be a gas phase volume. Now, at a certain point, this is going to end. I can continue decreasing the temperature, but then you are going to observe cavitation. It's going to collapse. And that's what is going to happen now. So you see now the formation of very many small bubbles of a gas phase. So there was cavitation, so the collapse of the metastable state. So this is the way we use to produce negative pressures. Now, if we want to see, there was someone here that would put the sound. that okay? So this is, you cannot see the tube very well, but there is, that capillary tube is inside an NMR tube. And we are decreasing the temperature, so we are in the negative pressure region. And at a certain point, the liquid is going to collapse. I think this, let's see if this works. Have you heard the noise? It's fantastic. Okay. Now you can ask me, how do we measure this negative pressure? Well, we can measure this negative pressure as we measure the positive pressure. For instance, if you have a Berthelot, what is called a Berthelot helix, so if instead of having a straight glass capillary tube, if you do a helix, right, and if you hang a sort of mirror at this lower bottom hand, if the liquid inside is at positive pressure, or if you are increasing the pressure, the helix is going to rotate this mirror on one direction. If the liquid is under tension, it will come in another direction. So you can use a laser beam, whatever, and project on a screen, have a scale, you calibrate in the positive pressure region, then you extrapolate, and you get your value of negative pressure. Now, when you wish to do this very accurately and changing temperature, the apparatus is very complicated. And also making these helixes is absolutely crazy. It's a crazy job. So we found out an alternative ways to estimate them. And how do you estimate? So if you are coming along a constant volume line, your isocore, that isocore, the slope, is represented by the thermal pressure coefficient, which is simply the ratio between the expansivity and the compressibility. We have tested this method of estimation, because then afterwards you can integrate just knowing your thermal pressure coefficient. So it's very simple. We have compared direct measurements with the estimation, and we are always within 1–2% difference. So we gave up on measuring directly. If we know the expansivity and compressibility of the liquid, we can estimate our negative pressure. Now, now I'm going to talk a little bit about nature. What you are observing here is a microscope photograph of the xylem of a mangrove tree compared to the size. So this is a photograph of our capillary. So this is the internal diameter, this is the external diameter. And this is really small. We are talking about less than sometimes 0.1 millimeters, right? Now compare what nature does. So nature is able to use much, much, much smaller capillaries, and that's why it's so efficient to find liquids under tension, aqueous solutions, in fact, in nature. For instance, our colleague have talked about tension, water under tension in plants, and from a thermodynamic point of view, when I see very tall trees, for instance, trees with heights of about as tall as 100 meters high, you have a difference of 10 bar between, let's say, the roots and the top of the tree. This is just hydrostatic pressure. But here you are at 1 bar atmospheric pressure. So up there, you have to have water at about -10 bar, which is a lot. It's not probably as much as that, but it's very close to this number. So this is impressive. And this is also another example. You know that octopus have this many suction cups. They have moisture, and I'm comparing this with a Walmart suction cup. Now, if you probably have already used Walmart's suction cups. If you don't use moisture on them, you can still, stick them to a wall. But then it's relatively easy, if there is only air inside, basically, it's relatively easy to pull it up. Now, if you fill your Walmart cup with water, and you do the same, first you stretch, and then you try to pull it up, you will not be able to do it. It's impossible, because the pressure is enormous. Because when you're trying to pull it up, the water is at negative pressure. It can build -3 bar, -4 bar, whatever. So do the experiment, it's very easy, and we will notice the difference between having water or any other liquid that adheres to the suction cup and to the wall. It will work also. Another example, the cracking, fingers cracking. Now I cannot do it, but I don't know, probably, I could hear it. This is another example of a liquid, in this case the synovial fluid, that is under tension, and when you do this movement, or the movements that are represented there, you are putting the fluid under tension, and then the metallic click that you hear is very similar to what I've shown to you in that capillary, that metallic sound. It's what you hear when you crack your fingers. So it's the collapse from the negative pressure to, it's the release of pressure from negative pressure to the liquid vapor equilibrium of your synovial fluid. Now, there are many things that we can do measure at negative pressure. For instance, this is an example of experiments that we did some years ago. These are isocores for water. For water, obviously, the isocore is not linear. It's linear somewhere here at positive pressure. But if you are close to the line of maximum density, then you have a minimum, and this is going up again, right? So you can measure by the minimum. This is the point of maximum density, and you can plot this against pressure. These are results for water and heavy water. So you can measure the continuation of the line of maximum density of water down to these metastable regimes. Another thing you can do is to phase separate a liquid solution, when it phase separates, obviously, into two liquid phases. So you can also observe if instead of a pure liquid you have a solution that has a tendency to phase separate, you can also provoke phase separation under tension. You can measure the speed of propagation of sound in a liquid. In this case, these were results obtained for water. Now, very quickly, why we are using ionic liquids? Because it's even much more easier to go into these negative pressure regimes, because they have a negligible vapor pressure. You cannot measure the vapor pressure of these salts at room temperature. They are highly viscous, so that also helps to maintain the metastable state. They are much more viscous than water. They have a relatively small surface tension. They have even a better adhesion to the walls of the container if the container is glass or quartz. They are even much easier to supercool, for instance, than water. And the last point, I'm not going to talk much about it because it's a detail of thermodynamics. The only thing I want to say is that in practice, you never get to the spinodal that I showed you in one of the first slides. Because the weakest point in these experiments is precisely, it's not the bulk of the liquid, because the bulk could sustain much higher tension, is the adhesion of the liquid to the container's wall. That's why otherwise we could go down to minus 3,000 bar, minus 4,000 bar, whatever. But practically, in practical terms, we are unable to do that. Very quickly, just to explain what is an ionic liquid, if we start with sodium chloride, the kitchen salt, we have a melting point of about 800 centigrade. So, but if I replace, for instance, the chloride by a larger, bulkier anion, I come down immediately to 260. This is impressive. And now, if I do the same and I replace sodium by, let's say, tetramethyl ammonium, I gain more, 100, and I'm already at 133. And finally, if I introduce some asymmetry in one of, be it in the anion or the cation. In this case, the combination of this cation with this anion gives me a salt with a melting temperature that is below the melting temperature of water. So we obtain what I could call room temperature liquid salt, which is the so-called ionic liquids. Now I have just to tell you something. The spirit of this conference is precisely to try to think on a way that is not orthodox. And about the ionic liquids, I have a story, very short story to tell you. We started to do research in this area in 2003. At that time, a lot of good laboratories in the world and fantastic scientists were already in place for 10, 20 years. And when I started reading about these liquid salts, they were always stating, well, they have no vapor pressure, it's impossible to put them in the vapor phase, so we cannot distill them whatsoever. And I said, no, I don't believe this. It may be possible. You just have to put this under high vacuum, increase a little bit the temperature. Well, they may decompose. Some may decompose, but those that are stable, I can distill them. And so this is a good example, in this case of success. We fought for, 2 years with nature about this and with their referees. It was a huge fight. I'm not going to give you the details. But anyway, we are able to demonstrate that we were right and that we could distill ionic liquids. Now, very quickly, coming back to the experiments. NMR. So what we are doing for the first time, I believe, is to get results for the diffusion coefficients, be it of salts, be it of water, be it of any other liquid, using this bipolar gradient pulse. I'm not a specialist on NMR, so this is a collaboration with my colleague that is the specialist in NMR. I'm just going to tell you that the results I'm going to show are going to compare. So here again, we have the vapor pressure line, liquid vapor equilibrium. This is one among many isocores. So each sample we use belongs to one isocore. It could be a little bit here to the right or to the left. And we are going to compare results of diffusion coefficients under tension, somewhere here at the red spot, with the corresponding values at the liquid vapor line. And this is a first example. It's for an ionic liquid, doesn't matter. So there is an anion and a cation, doesn't matter what it is. But you see that even in an absolute representation, you can see a difference between the points that are along the isocore, which are in blue, and those that are along the isobar. So the liquid, I'm calling isobar because ionic liquids don't have much vapor pressure, so it's a nominal zero pressure, constant zero pressure value. And even in a absolute scale, you can see immediately the difference. Now you can do in the differential scale. So now I have the ratio between the diffusion coefficient of the cation at the isocore. So the isocore is either at positive pressure or negative pressure, divided by the value along the isobar, which means the liquid vapor line. And as you can see now, it's evident that there is a huge difference between the diffusion coefficient at positive and negative pressure. So at positive pressure, obviously, the diffusion coefficient, as expected, is lower than on the vapor liquid line. And under tension, it's higher. So it means that we are expanding the liquid in very simple terms. It's more complex than that, but in very simple terms, we are expanding the liquid, and so we are increasing the mobility of the ions. I'm going to skip this and show just the same results, but in another representation. Instead of temperature, now we have pressure, but it's precisely the same. And I have results for another sample of the same ionic liquid. This is the same. And here it's probably important just to stop here for a moment. This is another ionic liquid, doesn't matter, but just to give you an idea of the effect. So this temperature is the filling temperature, right? So for higher temperatures than the filling temperature, we are at positive pressure. For lower, we are at negative pressure. And then the liquid collapses at a certain point, and you come back to your liquid vapor line. So the ratio between the diffusion coefficient of the cation under these two conditions is going to be 1. So this is the cavitation point. But look to the effect. So probably in the next one, because it's in pressure, look to the effect. So at about minus 10 megapascal, minus 100 bar, we have, if you extrapolate this a little bit, we have an effect of about 10%, which is a lot, right? So you can imagine that if you were at minus 1,000 bar, you would have an effect of 100% increase in the diffusion coefficient. So the first take-home message, while the expansion, the relative expansion, the delta V over V, when you are under tension, is not very high, it's only of about 0.5% per each 100 bar, the difference in the diffusion coefficient, the increase of the diffusion coefficient is of about 10%. The results that you have seen here for pure ionic liquids, we obtain very similar results for aqueous solutions of these salts in water. I'm going to skip this because this is a detail for thermodynamicists of ionic liquids, not important for today. Now, on water, results on water about the NMR. They are very strange. I'm going to tell you why. First thing, this is just the deviation of the proton peak, nothing else, but just this, along our isocore as we go into the negative pressure regime. So here, somewhere here is the filling temperature. We are going down in temperature. We are putting tension in our water, and you see a marked effect on the signal, the proton signal. Then there is the collapse of water somewhere here, and we are back in the liquid vapor line of water. So obviously, within the experimental error, you don't see any difference. Now, what is strange is this. What you are observing here is the diffusion coefficient of water against temperature, but the points that are here belong both to the isocore and to the liquid vapor line, right? So it means that we don't see any effect on the diffusion coefficient of water when we compared water under liquid vapor equilibrium with water either at a small pressure, well, small, of about 200 bar positive or minus 200 bar negative. So there is, all these points belong to both situations. But there is something interesting in this diagram. You see that there are two completely different regimes, because here you have a curvature between 10 Celsius and 40, 41, 42, and then a linear trend above that point. Probably you know that at about 40-something Celsius, there are other thermodynamic properties that have anomalies, like the pressure dependence of the expansivity, the temperature dependence of the compressibility, etc. And they occur at about this same point. So this has to do for sure with the change in the structure of water. People usually say, well, we are breaking, at a certain point we start to break a lot of hydrogen bonds. Probably is that, plus something else. So this is almost my last slide. So there is a marked downward shift in the peak of the proton, about 3 Hertz per each minus 100 bar, but no pressure or tension dependence of the diffusion coefficients, although two regimes are revealed. So there is a crossover of those regimes between 40 and 42 Celsius, more or less. We have to do more samples, but we have already 2 samples done, and they show this. Now, how can we explain this? I think there are 2 opposite effects here. If we think first about positive pressure, it is known that when we start to put pressure on water, the viscosity almost does not change. Well, in some cases, if you are at low temperature, it even starts to decrease, which is very weird, and then starts to increase. But, I mean, it doesn't change much, only above 500 bar or so. So I believe what is happening here is the combination of two things. So on one side, when you are at positive pressure, you are enhancing the repulsive forces. If you think about an intermolecular potential, if you are at positive pressure, you are decreasing the distance between the molecules, right? So you are on the side of testing your repulsive forces. While when you are with your liquid under tension, it's the opposite. You are screening, you are testing your attractive forces. But the point is that when you are at negative pressure and testing these attractive forces, you are increasing the volume, right? But at the same time, you are enhancing the structure of water. So the classes of water, you get more classes, you get water more structure. And these two effects, at least for a range up to 500 bar and minus 500 bar, are almost canceling, right? So this is the main conclusion, and also the main conclusion is that below 40 centigrades, water is really behaving like water, but above 40-something centigrades is behaving much more like an organic solvent. And I think with this, I'd like to thank you for your attention. And I'm sorry if I took too much time.
Thank you, Luis. You did extremely well. And water keeps all of us, I think, surprising us with this, for me, unknown properties. Unfortunately, there is no time for questions unless you risk your taxi. You have to say.
Well, one question.
One question.
If anyone has.
One question. Of course.
Yeah. Thank you for a nice and clear presentation. So I just wanted to mention our studies of EZ water. It turns out that the density of EZ water is higher than the density of bulk water. And so I could imagine, although it's not so obvious how, that if there's a transition between water and EZ water, that I'm wondering whether some of the anomalies that you've reported could somehow lie in this kind of transition, because if you have a closed container and for whatever reason you get a higher proportion of EZ water, I guess that could cause a kind of cavitation, for example. Mm-hmm. I'm just wondering out loud whether, for example, EZ water could be forming next to the capillary wall or chamber wall that you use.
Oh yeah, near the wall for sure, yeah.
Yeah, and simply because of the density difference between the two, mm-hmm. then the ratio of EZ to bulk water mm-hmm. could give rise to, I don't know, maybe some of these properties that you've reported. Yep. That's all.
Okay, thank you. Okay.
Okay, thank you very much. That was it.
Thank you.